Hello, folks. This is going to be your third installment of BCA tables, and this time we're going to be involving mass, and so we're looking at mass stoichiometry. So if we're looking at the first problem, or at least what stoichiometry happens to be, simply speaking, stoichiometry is working with ratios. All sorts of different professions use some type of stoichiometry in their job. Construction workers, for example, if they're going to be mixing up concrete, 3,000-pound concrete versus 4,000-pound sustainable concrete ends up being two entirely different recipes, or using ratios to make that happen. Baking is another way of using ratios. Cooking, hairdressers when they're mixing up hair dyes or preparing solutions for different type of processes. Engineers, and of course, chemists. Chemists are going to be using stoichiometry, and we've already started using that from the idea of the recipes when we've looked at BCA tables in the past. So now we're going to add the component of mass to it. So let's take a look at a sample problem. Magnesium reacts with hydrochloric acid to make magnesium chloride and hydrogen gas. What mass of hydrogen gas will be made from 48.6 grams of magnesium metal and 36.5 grams of hydrochloric acid? Well, the very first step of that particular issue is that we need to have some type of recipe. And in chemistry, as you know, the recipe is the balanced equation or balanced reaction. So take a moment. What's the balanced equation going to look like? I'll be kind enough to give you at least the formulas to start with. You should be able to balance that equation. So for the balanced equation, you should have gotten a ratios of 1, 2, 1, and 1 for the mole-to-mole ratio. All right, so now what? Well, now we have to figure out how much stuff we actually are starting with. And what are we talking about? Well, we've got 48.6 grams of magnesium and 36.5 grams of hydrochloric acid. Well, I cannot just stick those numbers directly into the BCA table, because this BCA table works off of particles or moles. And as we learned before, mass and moles, or mass and particles, are not the same thing. So we have to actually be able to convert those masses into moles first. So you'll notice that I've done the magnesium one for you. Took the 48.6 grams of magnesium, and I found the molar mass of magnesium on the periodic table, and I ended up converting those by dividing by 24.31. So the grams of magnesium are going to cancel, and I'm left with moles of magnesium, or in this particular case, 2.00 moles of magnesium. At this point, what I'd like you to try is and figure out how many moles are we going to have in 36.5 grams of hydrochloric acid. Take a moment to do that. So what you should have ended up with is 36.5 grams of hydrochloric acid ends up going to become 1 mole of hydrochloric acid. So now I have 1 mole of hydrochloric acid, and I have 2 moles of magnesium that I'm using to react together. And at this point, I have to figure out how I'm going to put that into the BCA table, right? Which is part 3. Fill out the BCA table. So this 2 moles of magnesium is what we got from the conversion that we did in the previous step. This 1 mole of hydrochloric acid is what we got from the previous step. And just as always, we have 0 grams of products before we start the chemical reaction itself. So if we've got 0 and 0, that's perfectly fine. We got 2 and the 1. Now, how do we fill out the rest of the BCA table? This is going to work the same way that we were doing last week. So what do? So you take the 2 and you divide it by the coefficient of the balanced equation, and you get a number. You take 1, you divide it by 2, and you get the ratio. So that way we can compare those ratios. So you'll notice that I now have 2 and 0.5. Out of those 2 values, the 0.5 ends up being the smaller one. Now, based off of that, we should be able to use that 0.5 and fill in the rest of the BCA table. Take a moment to fill in the rest of the BCA table. Here's what the rest of the BCA table should have looked like. You'll notice that I have negative 0.5 for the magnesium because the magnesium is a reactant and it's going away. I'm losing all of my hydrochloric acid, and we're producing a 0.5 mole both of hydrogen gas and magnesium chloride, which means after the reaction I have 1.5 moles of magnesium, 0 moles of hydrochloric acid, 0.5 moles of MgCl2, and 0.5 moles of H2 gas. So now what? Well, which piece of information will actually answer the question? So if we go back to the original question and we have the now filled in BCA table in front of us, we should be able to figure out what is the answer. Well, it's specifically asking what mass of hydrogen gas will be made from 48.6 grams of magnesium metal and 36.5 grams of hydrochloric acid. So here is the 0.5 moles of hydrogen gas that gets made, which then gives us, well, convert the 0.5 moles of hydrogen gas into grams, because the question didn't ask for it in moles, it did ask for what mass. I'll give you a moment to try and convert the 0.5 moles of hydrogen into grams. So you'll notice that we take the 0.5, the molar mass for hydrogen ends up being 2.016 grams of hydrogen, which gives us just about 1 gram of hydrogen gas. So now we've actually solved the problem. And you'll notice that we did go through 4 steps. We figured out a recipe first. We figured out what we had, and then we've put that into the BCA table and filled out the rest of the BCA table. Then lastly, we grabbed the information out of the BCA table and figured out what units we needed the answer in. So those are the 4 steps that we've got. I have 2 more sample problems I'm going to have you do as well, and I'm going to go through them one step at a time, but I'm going to give you a little bit more practice where you get to fly solo. So here's example problem number 2. It should also be on the page in front of you. Methane, or CH4, is burned. What mass of carbon dioxide is made when 50 grams of CH4 burns? So do step 1. Figure out the balanced equation. You should have gotten a balanced equation of 1, 2, 1, 2 for the mole-to-mole ratio. Now go ahead and take that 50 grams of CH4 and see if you can convert that into moles. Should have gotten 3.12 moles of CH4, right? So you'll notice that the conversion is there in front of you. Now you should be able to fill out the first row of the BCA table and also see if you can figure out what the 2 boxes up here are going to be as well. Give you a moment to do that. You'll notice that I ended up with the 3.12 moles of the CH4 like we had before. And you'll notice that since oxygen wasn't mentioned, oxygen's going to be assumed that we have an infinite amount of it, which is why I put the infinity symbol right here. Again, we have zeros for the products. And then for the top sections, well, 3.12 divided by 1 is going to be 3.12. Infinity divided by 2 is still going to be infinity. So at this point, you should be able to fill out the rest of the BCA table. Remember that the 3.12 is the smaller of the 2 numbers that you should use to be able to fill out the BCA table. All right, so here is the rest of the BCA table filled out. You've got a negative 3.12, negative 6.24, because we did the 3.12 times 2. And you'll notice the same thing over here. You'll notice that the infinity minus 6.24 is still going to be infinity. So 3.12 moles of CO2 is needed to be converted into grams to be able to get our final answer. I'll give you a moment to do that. So the 3.12 moles times 44.01 grams of CO2 should give you 137.3 grams of CO2. And that is going to be the answer that you need for that particular problem. We have 1 more sample problem left. Let's see how you do with this one as well. A 13.5 gram chunk of aluminum is combined with 25 grams of sulfur. It is heated vigorously. What mass of aluminum and sulfur remains? Just as before, step 1, balance the equation. Balance equation ends up being 2, 3, 1. At this point now, we need to convert both the 13.5 grams of aluminum into moles and the 25.0 grams of sulfur into moles. Take a moment to make both of those conversions. Those conversions end up giving you a half a mole of aluminum and 0.780 moles of sulfur. At this point, you have those pieces of info. You should be able to fill in that first row of the BCA table as well as that limiting reactant section at the top. So do both of those. You'll notice that we end up with 0.5 moles of aluminum and 0.780 moles of the sulfur. When I divide the 0.5 divided by 2, I get 0.25. When I divide the 0.780 divided by 3, I get 0.26. 0.26 is the bigger number, 0.25 is the larger one, so the 0.25 is what we're going to use to fill out the rest of the table. Take a moment to fill out the rest of the table and see how it turns out. Here's what you should have ended up with. You'll notice that we have minus 0.5 moles of aluminum, which leaves us with 0 moles of aluminum. We have 0.30 moles of sulfur remaining, and we were left with 1/4 mole of the aluminum sulfide. Now we got to figure out the answer though, because it did ask what mass of aluminum and sulfur remains. So figure out how many moles that happens to be first, and then we'll try and figure out how to get that into mass afterwards. So how many moles of aluminum and sulfur remain after the reaction? 0 moles of aluminum remain, 0.03 moles of sulfur remain. Now we get to convert those into mass. Take a moment to do that. You'll notice that you got 0 grams of aluminum. I didn't even have to show any work for that because 0 times whatever is still going to be 0 grams. The 0.030 moles of sulfur gets converted by multiplying it by the molar mass of 32.07 and gives us 0.9621 grams of sulfur. If you wrote down 0.96 grams, that would have been just fine. So now we've gone through 3 separate sample problems. Hopefully you did a bunch of that on your own and were able to get a lot of that correct. If you weren't, please let me know and I'll do what I can to try and help you out with it. I have given you a bunch of other sample problems to try, and if you have any questions on those, you should let me know. Hopefully this will help. If you need to watch this video more than once, I would recommend doing so. Have a good morning.